Hello everyone. In the previous session, we have discussed about Bernoulli's equation being applied to ideal fluid flow and some numericals based on it. Now we are going to discuss about the Bernoulli's equation for the real fluid flow. As you know, for ideal fluid, the viscosity term is 0, which means there is no friction factor, or I can say the fluid is inviscid or non-viscous. In that case, we can use a very simple equation, P upon rho g plus V square upon 2g plus Z is equal to constant, and that can be applied to any section. Suppose if I apply between two sections 1 and 2, the equation will be P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. We have already seen this. Now, in real life, the fluid is going to be subjected to friction factor, which means viscosity is something which is going to be present. Such kind of fluids are called as viscous fluid. They offer resistance to the fluid flow. Thus, there will be some losses in the system. So, for Bernoulli's equation for real fluid flow between the sections 1 and 2, when the equation is applied, the equation turns out to be P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus a term HL comes into picture. This HL is called as the loss of energy between the section 1 and 2. When I say that the loss of energy is added at the section 2, it simply means that my direction of flow is from 1 to the section 2. Let's take up an example to understand this concept. A pipe of diameter 400 mm carries water at a velocity of 25 meters per second. So the diameter of the pipe D is given as 400 mm, which is 0.4 meter, and the velocity V is given as 25 meters per second. The pressure at the points A and B are given as 29.43 Newton per centimeter square and 22.563 Newton per centimeter square respectively. So I have written pressure at A, PA is 29.43 Newton per centimeter square, which is converted into Newton per meter square by multiplying with 10 raised to 4. And the pressure at point B is given as 22.563 Newton per centimeter square, which again I have converted into Newton per meter square. The datum head at A and B are 28 meter and 30 meter. Find the loss of head between A and B. The datum head at A, ZA, is 28 meter given. Datum head at B is ZB, 30 meter given. We are supposed to find the loss of head between A and B. So if I say that the energy of the system at point A is EA and the energy of the system at point B is EB, what I am supposed to find is the loss of head, which means the difference between the head at point A and B. So I have written it as EA minus EB. Now how do we solve? This is just a small figure demonstrating what is given in the question. From the datum line, A is at a height of ZA and point B is at a height of ZB. At A and B, the diameters and velocities are given. Energy at A, EA is equal to PA upon rho g plus VA square upon 2g plus ZA. PA value is already given to me. Rho is 1000 because it is water. G is 9.81, which becomes 9810. VA value is already known to me, 25, and 2G, it is 2 into 9.81. ZA is known to me again, 28. If you substitute, you get the answer as 89.85 meter. Total energy at B, again EB can be calculated as PB upon rho g plus VB square upon 2g plus ZB. Again, if you substitute the values like above, you will get the answer as 84.85 meter. Therefore, the total loss of head between A and B, EA minus EB, is 89.85 minus 84.85, which is 5 meter, which is the required answer. See over here, energy at A is higher than the energy at B. And you can see there's a clear difference between the energy of both the sections. So there is a loss between A and B, which is of 5 meter, which is your HL term in the equation which we have written. And if this question is asked as to what is the direction of flow, we can say that the loss of energy is at point B. So the flow direction will be from A to B. Let's go to another question. A pipeline carrying oil of specific gravity 0.87 changes in diameter from 200 mm diameter at a position A to 500 mm diameter at a position B, which is 4 meter at a higher level. Now if you read, specific gravity of oil is given as 0.87. As you already know, for converting specific gravity of oil to its rho, you have to multiply with specific gravity of that particular fluid. Here the fluid is liquid, so I am multiplying with rho of standard liquid, which is water. So it becomes 0.87 into 1000, which becomes 870 kg per meter cube. Now if I draw the figure here, this is my datum line. Diameter is given as 200 mm at point A, and at point B the diameter is given as 500 mm. Also it is given that point B is at 4 meter height as compared to A. Now since what is A is not given, so I am assuming ZA as 0 and ZB is given as 4 meter. So at section A, DA is given to you, ZA is 0. At section B, DB is given to you, ZB is 4 meter. Let's read further. If the pressures at A and B are 9.81 Newton per centimeter square, so PA is given to you as 9.81 Newton per centimeter square, and PB is given to you as 5.886 Newton per centimeter square. I have converted here into Newton per meter square again. The discharge is given as 200 liters per second. So I am writing the discharge Q is 200 liter per second. For converting liter to meter cube, you will have to multiply with 10 raised to minus 3. Determine the loss of head and direction of flow. So you are supposed to find the first thing, loss of head, and second, the direction of flow. You know the equation of discharge. Q is equal to A1. You know the equation of discharge Q is A into V. So for section A, I have AA into VA. VA is what I need to find. Discharge is already known, 0.2. Area can be found pi by 4 d square. This is the answer for VA. Similarly for VB, I have used the equation A into V, and I get the answer for VB as 1.018 meters per second. The total energy at A can be found with P upon rho g plus V square upon 2g plus Z at section A. Substitute the values, get the answer. Total energy at B can again be found as P upon rho g plus V square upon 2g plus Z at section B. Substitute the values, get the answer. You can see a clear difference in values of the energy at the 2 points. So at A, I have 13.557, at B, I have 10.948. The loss of head will always be the difference between the two energies which I have obtained. Here the answer is 2.609 meter. As you can see that your EA is greater than EB, so obviously the flow has taken place from A to B, and hence the loss is at the end of B. So here I have just written, since EA is greater than EB, therefore the flow of fluid is from A to B. Thank you.